Hi, welcome to iEducator. This is Teacher Jeff. I'm an educator and an engineer by profession. And today we will discuss another chapter, and that will be chapter 6, which is all about sequencing. Now, in this lesson, there are three key areas that I'm going to be highlighting today. First, we have the introduction. Second, we have the problem or definition, and this includes key areas or sub-key areas. We have assumptions made in the sequencing problem. We have the applicability or the applications of sequencing problem in the real world, and we also have types of sequencing problems. And finally, I will also be discussing the solutions for sequencing problems or the different ways on how to solve sequencing problems. Now, in the previous chapters, if you can notice, we have dealt with problems where two or more competing candidates are in race, right? For using the same resources and how to decide which candidate or product is to be selected so as to maximize the returns or minimize the cost. Now, let us look to a problem where we have to determine the order or sequence in which the jobs are to be processed through machines so as to minimize the total processing time. Here, the total effectiveness, which may be the time or cost that is to be minimized, is the function of the order of sequence. And such type of problem is known as sequencing problem. So what do we mean by sequencing? If we say sequencing, it is the selection of an appropriate order in which a number of jobs or operations can be assigned to a finite number of service facilities or machines or equipment so as to optimize the outputs in terms of time, cost, or profit. So in case there are 3 or 4 jobs are to be processed on 2 machines, it may be done by trial and error method to decide the optimal sequence. For example, we have the method of enumeration. And if we say method of enumeration, here in the method of enumeration for each sequence, what we actually do is we calculate the total time or cost and search for that sequence, which consumes the minimum time and select that sequence. Now, this is possible when we have small number of jobs and machines, but if the number of jobs and machines increases, then the problem becomes complicated. It cannot be done by method of enumeration. For example, consider a problem where we have n machines and m jobs, then we have n factorial raised to the power of m. So theoretically possible sequences. For example, supposing the value of our n is 5 and the value of our m is also 5, then by plugging in the values to our formula, the result will be 23 billion possible sequences. Now, as you can see on the result, it is apparent that it is time consuming to find all the sequences and select optimal among all other sequences. Hence, what we need to do is that we have to go for easier method of finding the optimal sequence. Now, let us discuss the method that is used to find the optimal sequence. And before we go for the method of solution, we shall define the sequencing problem and types of sequencing problem. Here, the students have to remember as well that the sequencing problem is basically a maximization problem or minimization problem. Now, the next key area that I'm going to be discussing right now, that would be the problem or definition. So as you can see, this is our general sequencing problem. A general sequencing problem may be defined as follows. Let there be n jobs. Suppose we have job 1, job 2, job 3 until job n, which are to be processed on m machines. We have A, B, C, and so on, where the order of processing on machine, for example, A, B, C means first on machine A, second on machine B, and third on machine C. Or CBA means first on machine C, second on machine B, and third on machine A, etc. And the processing time of jobs on machines, or the actual or expected, is known to us. Then our job is to find the optimal sequence of processing jobs that minimizes the total processing time or cost. Hence, our job is to find that sequence out of n factorial times m sequences, which minimizes the total elapsed time, such as time taken to process all the jobs. The usual notation used in this problem are A sub I. A sub I refers to time taken by the ith job on machine A, where I is equal to 1, 2, 3, and so on. Similarly, we can interpret for machine B and C. For example, we have B sub I and C sub I, etc. And also we have capital letter T, which refers to total elapsed time, which includes the idle time of machines, if any, and setup time and transfer time as well. Now, we also have different assumptions that are commonly used in sequencing problems. So the principal assumptions made for convenience in solving the sequencing problems are as follows. First, we have the processing times A sub I and B sub I, etc. are exactly known to us, and they are independent of order of processing the job on the machine. Now, that is whether job is done first on the machine, last on the machine. The time taken to process the job will not vary, it remains constant. And for the second assumption, the time taken by the job from one machine to other after processing on the previous machine is negligible. So what do we mean by this? This means that we assume that the processing time given also includes the transfer time and setup time. And the next assumption, for the third assumption, each job once started on the machine, we should not stop the processing in the middle. Meaning to say, what I mean about this is that it is to be processed completely before loading the next job, okay? And the next assumption we have, the job starts on the machine as soon as the job and the machine both become idle, or if we say idle, we mean to say vacant. So in other words, this is written as job is next to the machine and the machine is next to the job. This is exactly the meaning of transfer time is negligible. And next we have, no machine may process more than one job simultaneously. This means to say that the job once started on a machine, it should be done until completion of the processing on that machine. And next we have the cost of keeping the semi-finished job in inventory when next machine on which the job is to be processed is busy is assumed to be same for all jobs, or it is assumed that it is too small and is negligible. That is, in process inventory cost is negligible. And next we have, while processing, no job is given priority. For example, the order of completion of jobs has no significance. This means to say that the processing times are independent of sequence of jobs. And finally, there is only one machine of each type. Now, the next sub-key area that we're going to be discussing right now, that would be the applicability or the applications of sequencing problem in the real world. Now, as you can see on our presentation, there are two applications of sequencing problem. First, it can be applied in job shop, and second, it can also be applied in batch production shops. Now, what do we mean by job shops and batch production shops? Now, if we say job shops, it is a type of manufacturing process in which small batches of a variety of custom products are made. In the job shop process flow, most of the products produced require a unique setup and sequencing of process steps. Now, job shops are usually businesses that perform custom parts manufacturing for other businesses. However, examples of job shops include a wide range of businesses. We have a machine tool shop, a machining center, a paint shop, a commercial printing shop, and other manufacturers that make custom products in small lot sizes. These businesses deal in customization and relatively small production runs, not volume and standardization. Okay, so this is where sequencing problem can be applied in the real world for those companies or small organizations which are under job shop production. And secondly, it can also be applied in batch production shops. What do we mean by this? If we say batch production shops, it is a method used to produce similar items in groups, stage by stage. In batch production, the product goes through each stage of the process together before moving on to the next stage. Now, the degree to which workers are involved in this type of production actually depends on the type of product. It is common for machinery to be used for the actual production, and workers participate only at the beginning and end of the process. Examples of organizations or companies that actually employ batch production shops, we have bakery businesses, we have textiles, and we also have furniture businesses. And the next sub-key area that we're going to be discussing right now, that would be the different types of sequencing problem. Now, there are various types of sequencing problems arise in real world. All sequencing problems cannot be solved. Again, please be reminded that all sequencing problems cannot be solved. Though mathematicians and operations research scholars are working hard on the problem, satisfactory method of solving problem is available for few cases only. Now, the problems which can be solved are n jobs are to be processed on two machines, say machines A and B, in the order AB. If we say in the order AB, this means that the job is to be processed first on machine A and then on machine B. And another problem which can be solved is n jobs are to be processed on three machines, machines A, B, and C, in the order ABC. If we say in the order ABC, what we mean about this is that the job is to be processed on machine A, second on machine B, and finally on machine 3. And another problem which can be solved is M jobs are to be processed on M machines in the given order. And finally, 2 jobs are to be processed on M machines in the given order. Okay, so these are the 4 different types of sequencing problems that we have. And the next key area that I'm gonna be tackling right now, that would be the solutions for sequencing problems. So what are the different ways in order to solve sequencing problems? As you can see, these are the following methods or ways on how to solve sequencing problems. First, we have n jobs and 2 machines. Under this, we have the analytic method. Second, we have sequencing of n jobs and 2 machines. And there are also cases that we have sequencing of n jobs and 3 machines. Next, we have processing of 2 jobs of m machines. And under this, we have 2 different methods. We have the graphical method, and we also have the enumerative method. And finally, we have the traveling salesman problem. And under this, we have the cyclic problem and the acyclic problem. Now, in this case, we will be focusing more on the first method or way in solving the sequencing problems, which is n jobs and 2 machines. Now, in order for us to better understand this, let us have an example. Okay, example, there are 2 jobs. We have jobs 1 and 2. These jobs are to be processed on 2 machines. We have machines A and B in the order AB. Okay, if we see in the order AB again, the job should be processed first on machine A and then on machine B. Job 1 takes 2 hours on machine A and 3 hours on machine B. And job 2 takes 3 hours on machine A and 4 hours on machine B. Now find the optimal sequence which minimizes the total elapsed time by using Gantt chart. Now, if we try to tabulate our problem, this will be our tabulation. Okay, this is how the tabulation looks like. So we have 2 columns, or 3 columns rather. We have columns for the job, and we also have columns for the machines. And remember, take note that time is in terms of hours. And based on our problem, we have 2 jobs, job 1 and 2, and we also have 2 machines. We have machines A and B. Now remember, job 1 can be processed in machine A for 2 hours and machine B for 3 hours. And job 2 can be processed in machine A for 3 hours and machine B for 4 hours. Now, if the problem given has 2 machines and 2 or 3 jobs, then it can be solved by using the Gantt chart method. But if the number of jobs are more, then this method becomes less practical. Now, if we say Gantt chart consists of x-axis, on which the time is noted, and y-axis, on which jobs or machines are shown. Now, for each machine, a horizontal bar is drawn, and on these bars, the processing of jobs in given sequence is marked. And let us take a small example and see how Gantt chart can be used to solve the same. Now remember, we are tasked to find the optimal sequence which minimizes the total elapsed time by using Gantt chart. Now the first step that we need to do is to draw x-axis and y-axis. So in this case, our x-axis should represent the time, and our y-axis should represent the 2 machines, okay? So represented by 2 bars. So this is our step number 1 in solving the said problem, okay? We have step 1. All we need to do is to simply draw an x-axis and y-axis. And again, I would like to reiterate our x-axis represents our time in terms of hours, and our y-axis represents our machines. We have machines A and B. Now, after this step, the next step that we need to do is to mark the times on the bars to show processing of each job on that machine. Okay, this will now be our step number 2. So for that matter, let us focus first our attention to machine A. Okay, so based on our problem, remember that job 1 can be processed in machine A for 2 hours, and in machine B, it can be processed in, again, this is step number 2. So what we're gonna do in step number 2, we need to mark the times on the bars to show the processing of each job on that machine. Now, as you can see in our graphical presentation, we have two axes. First, we have x-axis, which represents our time in terms of hours. And the second axis, that would be our y-axis, where we can see our machines. So in this case, you can see their machines A and B. Now, based on our problem, remember, there are two jobs. We have job 1 and job 2. And as you can see on our graphical presentation, our job 1 represents the bar with a colored orange, and our job 2 is represented by colored green bar, okay? Now, remember, based on our problem, they are to be processed. Both of these jobs, jobs 1 and 2, are to be processed on two machines, right? Machine A and machine B in the order of AB. Meaning to say, if we say in the order of AB, this means that job 1 or the jobs, both of the jobs should be processed on machine A first and then machine B. Now remember, job 1 takes 2 hours on machine A. So if we try to look at our x-axis, so we have the origin 0 and then 1, 2. So that means to say, job 1 is processed on machine A within 2 hours or at 2 hours exactly. And remember, our ordering is AB. Now, since we are done with machine A, job 1 will now be processed to machine B. And since we stopped at 2 hours, so our starting point is 2 hours. And remember that in machine B, it will take machine B to process job 1 for 3 hours. So if we check the count with our starting point 2, so we have 3, 4, 5. Okay, so meaning to say, job 1 is processed in 3 hours using machine B. And going forward to job 2, so for job 2, based on our problem, okay, if we try to go back to our problem, here it says job 2 takes 3 hours on machine A and 4 hours on machine B. Okay, let's try to go back to our graphical presentation. And so we will have a visual on our presentation. Okay, now since we are done with job 1, it is now time for us to plot our job 2 in our Gantt chart. Now, since job 1 is done, job 2 is processed in machine A first, given that our sequence is, or order rather, is AB. Meaning to say, we will process this one on machine A first and then to machine B. Again, as you can see, since we are done with job 1, so we ended at second hour. So second hour will be our starting point for job 2. And like what our problem said, this will be processed by machine A for 3 hours. So if our 2 is our starting point, and if you will try to count the hours, 3, 4, 5. Okay, we stopped at 5th hour. Okay, so meaning to say job 2 has been processed by machine A for 3 hours. And after that, since we are done with machine A, that it will be processed now with machine B for 4 hours. Now, since we are done with job 1 and we stopped at 5th hour, therefore, the 5th hour will be our starting point, and we will try to count 4 hours. So from 5, we have 6, 7, 8, 9. Okay, so we stopped at 9. Okay, so that is how we plot our bars to show the processing times of each job on that machine. Now, as you can see on our graphical presentation, we can conclude that both the sequences show the elapsed time of 9 hours. The only drawback of this method is for all the sequences, we have to write the Gantt chart and find the total elapsed time and then identify the optimal solution. this is very laborious and time-consuming. Now, if we have more jobs and more machines, then it is tedious work to draw the chart for all sequences. And therefore, we have to go for analytical methods to find the optimal solution without drawing charts. Okay, so since we need to find another method without drawing charts, or like we did earlier, which we make use of Gantt chart, now we will try to look at analytical method. Now, if we say analytical method, it is a method that was developed by Johnson and Bellman for simple problems to determine a sequence of jobs which minimizes the total elapsed time. Now, the method and jobs are to be processed on two machines A and B in the order AB. For example, each job is to be processed first on A and then on B, and passing is not allowed. That is, whichever job is processed first on machine A is to be first processed on machine B also. Whichever job is processed second on machine A is to be processed second on machine B also, and so on. That means that each job will first go to machine A, get processed, and then go to machine B and get processed. And this rule is known as no passing rule, meaning to say you really need to go to have your job processed first on machine A and then on machine B, especially if our order is order AB, okay? And second, the problem Johnson and Bellman method concentrates on minimizing idle time of machines. If we say idle time of machines, this is where when our machines are vacant, they are not used, they are unproductive. Now, Johnson and Bellman have proved that optimal sequence of n jobs, which are to be processed on two machines, A and B, in the order AB, necessarily involves the same ordering of jobs on each machine. Now, this result also holds true for three machines, but does not necessarily hold true for more than three machines. So, meaning to say, our maximum number of machines that we can cater in this method is only three machines. We can no longer do four machines or more. And therefore, the total elapsed time is minimum when the sequence of jobs is same for both the machines. And third, let the number of jobs be 1, 2, 3, and so on. Now, the processing time of jobs on machine A be A sub 1, A sub 2, A sub 3 to A sub n. And the processing time of jobs on machine B be B sub 1, B sub 2, B sub 3 up until B sub n. And fourth, Johnson and Bellman algorithm for optimal sequence states that identify the smallest element in the given matrix. If the smallest element falls under column 1, for example, under machine 1, then do not job first, as the job after processing on machine 1 goes to machine 2, it reduces the idle time or waiting time of machine 2. And if the smallest element falls under column 2, for example, under machine 2, then do that job last, okay? So next, this reduces the idle time of machine 1. For example, if rth job is having smallest element in first column, so as you can see on the graphical or tabular presentation at the bottom corner or part of the text, okay? So again, for example, if the rth job is having smallest element in first column, then do the rth job first. However, if s job has the smallest element, which falls under the second column, then do the s job last, okay? Hence, the basis for Johnson and Bellman method is to keep the idle time of machines as low as possible and continue the above process until all the jobs are over. And fifth, if there are n jobs, first, write n number of rectangles as shown in the previous slide, okay? This one at the bottom part. And whenever the smallest element falls in column 1, then enter the job number in first rectangle. If it falls in second column, then write the job number in the last rectangle. Once the job number is entered, the second rectangle will become first rectangle, and last but one rectangle will be the last rectangle. And sixth, now it is time for us to calculate the total elapsed time as discussed. And we need to write the table as shown. So let us assume that the first job starts at 0th time. Then add the processing time of job first in the optimal sequence and write in out column under machine 1. So this is the time when the first job in the optimal sequence leaves machine 1 and enters the machine 2. Now add processing time of job on machine 2. So this is the time by which the processing of the job on 2 machines over. So next, consider the job which is in second place in optimal sequence. So this job enters the machine 1 as soon as the machine becomes vacant. For example, first job leaves the second machine. Hence, enter the time in out column for first job under machine 1 as the starting of job 2 on machine 1. Continue until all the jobs are over. And be careful to see that whether the machines are vacant before loading. So total elapsed time may be worked out by drawing Gantt chart for the optimal sequence. And finally, we have points to remember as well, especially if we will employ this method. Remember, if there is a tie, for example, we have smallest element of same value in both columns, then minimum of all the processing times is A sub R, which is equal to B sub S. For example, minimum A sub I, B sub I equals A sub R equals B sub S. Then do the Rth job first and S job last. And second, if minimum A sub I, B sub I equals A sub R, and also A sub R is equal to A sub K, say, here, tie occurs between the two jobs having same minimum element in the same column. So first column, we can do either Rth job or Kth job first. There will be two solutions. When the ties occur due to element in the same column, then the problem will have alternate solution. If more number of jobs have the same minimum element in the same column, then the problem will have many alternative solutions. So if we start writing all the solutions, it is a tedious job. And therefore, it is enough that the students can mention that the problem has alternate solutions, okay? And the same is true with B sub i's also. If more number of jobs have some minimum element in second column, the problem will have alternate solutions as well. All right, I think that's a good place to stop. If you have questions, please let me know on the comment section below. And if you like this video, please don't forget to subscribe and hit the bell button for the latest updates. Thank you.